students. This video is focusing on AOI design and specifically how we build truth tables and determine how circuits work from truth tables. We also look at the reverse of that. How do we take a logic statement and turn it into a truth table so we know what's happening? And then lastly, how do we take a scenario or a word problem and break it into a function statement and a truth table? This video is pretty long, I'm sorry for that, but most of it is us working through examples and going over the answers to them. It's super important that you pay attention to those examples because they're just like the ones you'll be working through in your assignment. All right, let's get started. Okay, so this lesson is 211 and it takes a look at AOI design, and specifically taking truth tables to logic expressions. So what we're going to do in this presentation is we are going to learn how to actually properly construct a truth table. You guys have been given truth tables before, but you haven't made any. And then you are going to learn how to write a sum of products logic expression from a truth table. So basically, how does the circuit work, and write that in a logic expression statement, and then how to do the reverse of that. How do we go from the expression to the truth table? And then how do we create all of that from a word problem? So first of all, when we construct a truth table, we need to know that a truth table shows a logic design's output and how it responds to all the possible combinations of inputs. So the truth table is showing us all the possible combinations of inputs and then how the circuit responds to those inputs to get a specific output. So logic design with n inputs will have 2n input combinations. So if we have 10 inputs, we'll then have two 10 input combinations that we need to work with. Or 2 times 10. So the inputs are listed in binary order, so in counting order. So I pointed that out in our last lesson when we were looking at the truth tables, is that we always start at 0, 0, 0, 0, 0, 1, and we put them in counting order in our columns to the left to identify our inputs. And then the outputs are always listed in our columns to the right. Now, most logic circuits can have more than one output, so we need to be careful how we're building our truth tables, because sometimes we need to have output 1, output 2, etc. So let's look at an example of a truth table. So here we see that we have X, Y, Z, and then F1 or function 1 is our actual output. So we have 3 inputs, which means we have a total of 8 combinations that we're working with. So 8 equals 2 to the third because we have 3 inputs, so it's 2 to that power. So when we look at our inputs, they're counted in binary order, 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. through the possible combination. So that's how we know how many rows we need in our column, is we need a total of 8 because of the total number of combinations. We then have our output to the right, and this is simply what is happening when we have that logic. So when we're looking at this and going through, that's how we know, obviously by going through the circuit, how we know what F1 is. So truth tables can be big, small, they vary. So if we have a 2 input, this is what a 2 input looks like. So again, 2 to the second, so we have a total of 1, 2, 3, 4 rows. If we have 3 inputs, we have 8 rows, and then if we have 4 inputs, we're looking at 16 different combinations and 16 rows. So the more inputs you have, the larger the truth table is going to be. So what do we do with this so that way we can verbally explain how our circuit functions? So we have to write something called a min-term. So a min-term is what we see right over here, and it is basically just a written expression of the highs and lows through the lens of the input. So we write a min-term adjacent to every row in the truth table that has a 1 or a high signal in the output column. So if we look at this example down here, we have 0, 0, 0, that's a low. 0, 0, 1, the output's a 1. So therefore we need to write a min-term for this. And basically what this is telling us is X not, because X is a 0, Y not, because Y is a 0, and Z get us a high signal. So that's the expression. So this is so after we write all of the min-terms for any row that has an output of a 1, we then need to combine them together to create something called a sum of products logic expression. So basically we are combining all of these together to be able to express what is happening in our circuit. So if we look at this, this is our SOP logic statement. And so what this is saying is that F5 is equal to X naught, Y naught, Z, or specifically or, x naught, y, z, or x, y naught, z naught, or x, y, z naught. So those are the combinations of inputs that will give us a true statement in F5. So that's what we're looking at. So let's take a moment and look at an example. So right now we have a truth table and you need to write the logic expression for F6. So again, you're going to start by looking at the outputs, and any row that has a 1 is where you have to write a min term. Then you have to combine those min terms into the SOP expression. So take some time to work on that, and then we'll go over the answer. Okay, so let's take a look at what this SOP logic statement would be. So the first row that has a high is right here, and that min term is A naught, B naught, C naught, D gets us a high signal. Then we go down to our next one where we have a 1, and this is A naught, B naught, C, D, and that gets us a high signal. Then we have 3 more down here. So this one is A, B naught, C, D. Our next one is A, B, C naught, D, and then A, B, C, and D. We then have to combine these by saying F6 is equal to, and then we string all of the min terms together to be able to create that full SOP statement. Okay, so let's stop for a second and talk about some of the symbols that we're seeing in this video. First of all, I keep saying A naught or A, okay? So we have 2 different symbols here. One, there's no symbol at all, and then we have this bar above it. Anytime we see a bar above an input, whether it's A, B, C, X, Y, or even Z, that bar means not. So that means that we are indicating this as a 0. Anytime that we just have a letter, whether it's A, B, C, X, Y, etc., this is indicated as a input of high, which means we get a 1 in the truth table. So now, how do we do the reverse of that? How do we take a logic expression and create a truth table from it? So if we were given this to design our circuit, how do we work backwards to create it? Well, so for each term in the logic expression, we have to place a 1 in the output column for the input conditions that match the midterm. Some terms match more than one input condition, so we just have to be careful when we're writing it. So let's take a look over here. So we know that we have a total of 3 inputs from this statement. We have an X, we have an Y, and we have a Z, because that's what's visible. So we label our inputs X, Y, and Z, and F7 is our output. Then we go through, and we need to, because we have 3 inputs, we know that we have a total of 1, 2, 3, 4, 5, 6, 7, 8, because 2 to the third gives us 8. So we then fill in the binary count for those 8 rows. So we go from 0, 0, 0 to 1, 1, 1. Then what we need to do is read along with our expression table. So right here, our first expression is X naught, Y naught, Z naught. So that's 0, 0, 0. So 0, 0, 0 gives us a 1. We put a 1 in that spot. The next one is X, Z. Notice that Y is not listed here. That means that both this row, where we have the X and Z, and the bottom row, where we have X and Z with 1s, both get a high signal because Y is not added in here. So anywhere where X is 1 and Z is 1 gets a function output of 1. Then the last expression we're looking at is X naught Y Z. So we need to find X naught, okay, Y, and Z, and that gets a final 1. After we filled in those, every other row gets a 0 because it's not listed inside of the SOP statement. So we've taken a look at the different symbols and terminology inside of SOP logic statements, but the real question is how do we write them or type them in Google Docs? Handwriting is super easy. We can just draw a line over top of our letters to indicate the input and whether it is a regular letter or we're symbolizing not. Same thing with the plus sign and the multiplication sign for or and. Now, in Google Docs, it actually makes it super easy. If we open a new Google Doc and you go to View, Show Equation Toolbar, you will get this lovely toolbar right here. Some of you may have used this in math classes before, but let's go back and visit that equation that we worked on before. So if we have, or that SOP statement we worked on before. So if we have F1, that means I need to format my text, and I want it to be a subscript for F1. In order to get my subscript off, format text, I just uncheck my subscript, it goes back to normal, equals, and then I have an X naught. So how do I get the X naught to appear with the bar over it? Well, I'm going to click on New Equation, and I'm going to hit /. This is typically above your return key. It's not a standard slash. It has to be going in this direction. So make sure you're looking at your keyboard to make sure you're choosing the right slash. So you're going to choose / overline, and then we're going to push the space bar on our keyboard. You'll notice that a bar has now appeared, and I can type whatever letter I want. So I can hit X naught, and I can also type Y naught. Now, I can leave this like this, or I can do two different variables. I prefer to use them as two separate things because right now, X, Y is not a combined input. Later on, we're going to deal with more complex circuits where X and Y are actually its own input. So we need to separate these. So I'm going to hit the Enter key twice, and it leaves it there. I'm now going to do that again for my Y. So I'm going to hit that / overline, push my space bar, and I've got Y naught, enter twice, and I'm good to go. Then I have Z plus, shift key, and then the equal sign, plus, XZ, plus, here we go again. I'm going to insert new equation, overline, space bar, there's my Y naught, and there's my Z. Now you'll notice I typed those in lowercase letters. That's fine. However, when we get into more complex equations, you may want to use capital letters because they're easier to read. So let's give this a try. So you're going to make a truth table for the following logic statement. So F8 is your output, and we have A, B, C, and D as input. So that's a 4-input truth table. So you have to start by identifying the inputs A, B, C, and D, and F8 in columns. Because it is an 8-input truth table, you need to list however many rows you need and then fill it in with a binary count. You are then going to go through here and identify which rows get a high signal based upon these expressions. Take some time to figure this out, and then we'll go over the answer. Okay, so let's go over this together. So we started with F8 equals A, B naught, C, D, or A naught, B naught, or A, B naught, C naught, D naught, or B, C naught, D. So let's start by looking at how we set up the truth table. We labeled our inputs A, B, C, and D, and then our output as F8. We then went through and we created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 rows in our table. You then need to count to 16 in binary by filling in 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, etc. down to 16. So we need to look at this first expression. So we have A, B naught, C, D, which means we have 1, 0, 1, 1. So we need to find a row where we have 1, 0, 1, 1. So if I start looking, here are my ones. There's my 1, 0, nope, 1, 0, nope, up, 1, 0, up, not quite, 1, 0, 1, 1. There it is, A, B naught, C, D. Then I have to look at A naught, B naught. Any row where A is a 0 and B is a 0 gets an output of 1. So that means this entire section right here gets an output of 1 because A and B are both 0. My next expression is A, B naught, C naught, D. So 1, 0, 0, 0. So I need to find the row that's 1, 0, 0. 1, 0, 0, 0 gets a high of 1. My last one is B, C naught, D. So any row where D is a 1, B is a 1, and C is a 0 gets indicated as a high signal. So that's down here and up here we have instances of that. After you've filled in all of those high signals, just fill in the rest with the low signals or zeros and you're good to go. So how do we go from a word problem to a truth table? So first of all, when we read the problem, we have to identify the number of input variables. Then we have to assign the variable's name, so A, B, C, D, etc., and establish the assignment condition for each variable. So what that means is that what does a 0 or a 1 mean for that input? We then create the truth table from there. So let's take a look at an example. Let's say a large fuel tank has sensors that monitor temperature and pressure. Both sensors output a low if they are within a safety range, meaning they're not triggering anything. They're low, we're safe. An alarm will sound if either sensor indicates an unsafe condition is present. So that means that if A or B are high, then we get a high output. So we need to create a truth table for this logic design. So if we label P for the pressure sensor, T for the temperature sensor, and then A is our output for our alarm, we have our 3 inputs. Because it's 3 inputs, we know that we have 4 rows. So we fill in with our binary count, 0, 0, 0, 1, 1, 0, 1, 1. Now we need to break down our statements. So if the pressure sensor is off, we're safe. If it's on, it's unsafe. If the temperature sensor is off, we're safe. If it's on, we're unsafe. Again, if the alarm is 0, then it's off. If the alarm is on, then the alarm is going off. So we know that any condition where P has a 1 or T has a 1 is going to trigger the alarm. So we need to look through the columns and go, okay, that's a 1, there's a high signal. There's 1, that's a high signal. Both of them, still a high signal. So let's do an example, okay? Your teacher keeps her final exams in her office. For security reasons, she would like you to design an alarm system for her office. The office has a window and a door that are equipped with sensors that output a 1 when they are secured. So when they're closed, they have a 1. When the alarm system is turned on with a key, the siren should sound if either the window or the door is insecure or open. So if they switch to a 0, this alarm should sound. So take a moment, work through this problem. Remember, the first thing that you're doing is identifying your inputs, determining how many rows are in the truth table, completing your binary count, then determining the conditions that require a high signal. Okay? Take some time and then we'll go over the answer. Okay, so here's our answer for number 3. So first of all, the assignments. If we have a key that's 0, the system's off. And if the key is on, then the system is on. So that's a 1. So that's one of our inputs, is the key. We also have the door sensor, which we've indicated with the letter D. 0 is open, 1 is closed. Then we have the window sensor, so 0 is open, 1 is closed. And last we have the siren, where 1 is on and 0 is off. Looking at this statement, we know that there's a specific combination of things that have to happen in order for us to get a high signal. So right now, nothing is input, so we have a 0. If the window is on, but the key is not activated, then we have a 0. If the door is active, but the key is not, that's a 0. If the door and window are active, but the system has not been turned on by a key, we still have a 0. Now, if the key is indicated, and we have the door sensor open and the window sensor open, then the siren's going to go off. If the key is active and the window sensor is open, or the window sensor is closed, then the siren is on. Okay, so I know that was a lot to digest. We just went over 3 different things. We just covered taking a truth table and writing a logic statement, which I know is fun, different, weird, something we haven't done before. We also went over how we take an SOP statement and turn it back into a truth table. And then lastly, we looked at a word problem and how we convert that into both a truth table and a logic statement. I know this was a lot of information to digest. Feel free to re-watch the video again, come into Baron time, check-in time. I'm happy to work through some more examples with you. All right, I will see you guys in class. Bye.